Okay, in the last class we have discussed about the classification of elementary particles and the classification or grouping of hadrons. In that grouping of hadrons, we have first discussed about the um, Sakata model, and then we have discussed about the eightfold way. We will just start from that eightfold way here. So you can see here we have the in the eightfold way. First one is let's consider octet of semi-stable mesons. Okay, in that octet of semi-stable mesons, you can see this figure. There are eight particles, total eight particles, and this figure is you can see in y-axis you have strangeness, and in the x-axis you have I3 value. And in this octet, if you consider any meson which will be having spin of 0 and baryon number is 0 because it will be, these are not baryons, then you have the parity which is -1. All these numbers are important when you consider or when you check the interaction whether it is possible or not, or the possibilities or whether the interaction is conserved or not. Okay, such kind of questions. For that questions, you can have these different numbers you have to check. So if you consider the angular momentum, spin angular momentum, you have to consider for all the particles. Then if you consider baryon number conservation, then you have to consider the baryon number. Then for parity conservation, you have to consider this parity. That is -1 for these mesons. Okay. So in this, these numbers are important. And you can see this. There are four multipliers in this particular object. You have k0, k plus, and then you have pi minus, pi 0, pi plus. That is a triplet, second multiplet. Okay. And then you have a singlet here. That is theta 0, and the k minus k 0 bar are the next multiplier, which is nothing but a doublet. Okay. So these are the four multiplet, which is in that octet of semi-stable meson. So and correspondingly, you can also see the strangeness value for each of these particles. Okay. For k0, k plus, you have +1. For pi minus, pi 0, pi plus, you have 0 strangeness, and k minus k0 bar, you have -1 as the strangeness. Similarly, you can see in the x-axis, you can see the different I3 values. These are in the x-axis, you have I3 values. So this is I3 values. So when you consider that x-axis, you can check what are the I3 values or z component of isospin corresponding to each of these mesons. Okay. And now we'll move to the next octet, which is nothing but semi-stable baryons. Okay, octet of semi-stable baryons. You can see these baryons are having spin half. Okay. Then the baryon number is 1 because they are baryons. Then parity is +1. Parity is +1. And again, this also consists of four multiplies. You can see neutron and proton, that is doublet. And then you have sigma minus sigma 0, sigma plus. Then you have lambda 0, which is a singlet. Sorry, yes, lambda 0 singlet. And then you have this cascade minus and cascade 0, or psi minus and psi 0. So these are the particles which is inside this octet of semi-stable baryons. You have to remember this spin of these baryons are half. These are spin half baryons. Okay. Then now we'll move to the next group, which is nothing but the octet of mesonic resonances. We have already discussed about the resonances in the last class. So in the case of mesonic resonances, we have these particles K0 star. You can see here K0 star, K plus star. Okay, all these are resonance particles. These are extremely short-lived particles that you cannot determine uh, easily because they are having a very less lifetime. Okay, and they will produce some kind of disturbance in their surroundings. So from that disturbance, you can predict the presence of those particles. So that's why it's called a resonance particle. And these resonance particles, or if you consider mesonic resonances, this is the group corresponding to object of mesonic resonance. From here, you can see the spin of this mesonic resonances are 1, and baryon number is also 1. Then you have the parity, which is -1. Parity is minus 1. And you can also see the groups from here, and you can see this strangeness is 1 0 minus 1. You can see this axis corresponding to different particles. You can also see I3 values on the x-axis for the corresponding particles. If you are considering rho plus, okay, so this is the multiplet or triplet, that is the rho, which is a resonance particle. And for rho plus, you have the I3 value, which is 1. For rho 0 and 5, we have I3 value, which is 0. And rho minus, you have I3 value, which is minus 1. And K minus star, you have this minus half. Okay. All those things are. That is that's about mesonic resonances. Now, if you consider decouplet of baryonic resonance, uh, decouplet of baryonic resonance, you have to consider the spin value of decouplet of spin value of this baryonic resonances, which are the resonance particle which are baryons. Then you have the baryon number again, which is 1, and parity, which is plus 1. Okay. Because this one, I think, yeah, this one must be then 0. Okay. This baryon number, this has to be 0. Please check that. This one has to be 0 because it is mesonic resonance. You just check that. Okay. These are the values corresponding to the baryonic resonances, which are having spin of 3 by 2, baryon number 1, and the parity, which is even or positive. Okay, plus 1. Then corresponding decouplet, you can see here, baryonic decouplet, which consists of total of 10 particles. You can see delta family, which are resonance particles, delta minus, delta 0, delta plus, delta plus plus. These are the particles which is in that delta family. And also you can see in the vertical direction, you can see the charges of each particles. This is applicable to all these octet also. Okay, you can observe those charges along this vertical line. So delta minus. Then you have sigma star minus, that is the resonance particle of sigma. Then sigma star 0, sigma star plus, then cascade star minus, cascade star plus, cascade star 0. These are the resonance particle for cascade or psi particle. And then you have the omega minus. The omega minus, which is so you can see, so for the strangeness of the omega minus, which is minus 3. So this consists of 3 strange particles that we'll discuss while explaining the quark model. Okay, so this is the decouplet of baryonic resonances. So all these things are, you have to remember the strangeness of the particle and I3 of the particles. And if you know this figure, then you can easily say what are these values. Okay. Now we'll go to the model, quark model, and I think we should explain only the important portions of the quark model. So I'm not going to explain all the theory. So basically, the quark model suggests that all the hadrons are made up of uh, some more tiny particles, or fundamental particles, which are the quarks. And as you can see here, you have 3 different quarks listed here or tabulated here. You can see up quark, down quark, and strange quark. And the corresponding symbols are U, D, S. Okay. So these are the quarks which are used to make hadrons. Okay. That is the postulate. And then corresponding spin value of each quark you can see here, half, 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 which means the quarks are Fermi particles or fermions, so which are having half integral spin. And then you can see the charge of up quark is 2 by 3 e, and charge of down and strange quarks are minus 1 by 3 e. So when they are joined together, as we discussed earlier, for baryons, I think we didn't explain that. So for baryons, these are made up of three quarks, okay, three quarks, and for mesons, mesons are these are the hadrons, baryons plus mesons. So mesons are made up of two quarks, two quarks. Okay, and if you consider baryons, antibaryons, particles with antibaryons, which will be consist of three antiquarks. Okay, and in the case of mesons, these two quarks are made up of further. These two quarks are made up of one quark and antiquark pair. One of them will be quark, and the second one will be antiquark. So two quarks are there. One is quark, and the other one is its antiquark, not its antiquark. So this is nothing but quark plus antiquark pair. Antiquark pair. Okay. I will explain that later. So these are the values of charges, spin, etc. for corresponding to each quark, up, down, and strange. And then you have baryon number 1 by 3, 1 by 3, 1 by 3. So when you have three of these quarks, then your baryon number will become this baryon number will become 1. Okay, 1 by 3 plus 1 by 3 plus 1 by 3, that will make 1. If you consider antiparticles, so for example, anti-up quark, anti-down quark, uh, strange quark, you can see from here, you can have that and antiparticles of the quarks, up, down, and strange. And you can see the value of baryons, which are minus 1, or baryon number is minus 1. So that will make baryon number total is minus 1 if you are having anti-baryon. And if you consider mesons, then there will be having 1 by 3 and minus 1 by 3, because one particle will be quark, the other particle will be antiquark. That will make the baryon number equal to 0. So all mesons will be having the baryon number equal to 0. And the strangeness, you can see only the strange quark will be having strangeness, and that is minus 1. Okay, so the antiparticles you can see spin are same, and the only the charge you can see charge is minus 2 by 3 here. Here it was 2 by 3. Okay, so the charge will be opposite of the real particle, and also baryon number is also opposite, or it is negative of the real particle. Okay, similarly strangeness also you can see strangeness is plus 1 for anti-strange particle, anti-strange particle, or anti-strange quark. Okay. Now we'll just represent these quarks in that octet and decouplet form. So first one you can see octet of spin half baryons. Octet of spin half baryons. This we have discussed earlier. Spin half baryons we have already discussed. And then you have to consider the quark formula of each of these particles. Okay. You can see for proton, this first one is proton, this one is neutron. I hope you can see that. So for proton, you can see the quarks are UUD, 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 and for neutron it is UDD, UDD. Similarly, you can see for all the baryons with half spin, which is nothing but the octet of those baryons representation. You can that we have already discussed earlier. So each of those baryons will be having different quarks, and they will be having three quarks. For all the baryons, there will be three quarks. If you consider antibaryons, then there will be antiquarks. Okay. So in this case, you can remember this pattern. I will just show you how you can remember this particular group, or in that octet form. In that octet form, how you can remember all these quarks. That will I will just discuss. So you see, this is U. You just take in this octet form. You just take this arm as U. These two are U. Okay. Then you take these two arms are. These two arms you take as D, a D and D. You can take D also. This one also D, and this arm you take it as S. This is also S. Okay. So this side, this particular arm you take it as U. This particular arm you take it as D. This particular arm you take it as S. Then for baryons you have three chords. So you consider UU first for all these arms, DD, then DD, then SS. Okay. Then you just check what is the quark which is near to the given particle. Okay. So you have a proton here, and near to that proton you have neutron. Okay. If you move this side, if you move this side, then you have again U. Okay, that is not allowed. Three all are not same quarks for any of the baryons which are coming in these arms. Okay. So then you have to consider, you don't have to consider this side because there also you have U, so you don't have to consider that side, but you consider the other side, and the adjacent one is D. Okay, then you just put D here. That is the corresponding quarks, the quarks structure inside that proton. Okay, and correspondingly, if you consider neutron, where you have to look, you should not look at this side because here also you have D, here also you have D, so you don't have to look at this side. So this is not, this is the direction you have to look. Then you can see you have DD, then you have to take the third quark from this side, that is U. Okay, so DDU will be corresponding quark for neutron. And also you can check for others. For example, if you take this cascade 0, then you have SS in this arm. Okay, then where you have to look, you should not look in this side. This is not possible because already there is S, so you have to look at this side. So what is the adjacent quark or nearest quark to this SS? That is UU. Okay, so then you fill U here, then SSU will be the quark corresponding to that cascade. Okay, so just consider the nearest quark and fill it in this position, third position. Okay, then you will get the quark of the corresponding uh, particle or the baryons, half baryon with the spin half. Now we'll move to the next one, which is the mesons, spin zero mesons. And for spin zero mesons, this structure we have already discussed in this group object of mesons, spin zero mesons. Then here also you can just put the values for the arms, different arms. But remember that quarks are made, these mesons are made up of two quarks, and one of them will be quark, and the other one is antiquark. So it is a quark antiquark pair. Okay. So this side you can just put it as U. Okay, UU. This is DD and SS. Because we have only two quarks, one quark and the other one is antiquark, two particles which are used to build these mesons. So you don't have to consider UUDDSS here. Only you consider UDS as the first quark. And which one will be the second quark or antiquark of this? So when you consider K plus, you just look at the opposite quark or the quark at the opposite corner. You can see the opposite side, not the center one. The opposite edge you have the quark which is S. Okay, the quark is S. So you just put S bar because the second one will be the antiquark. So you just put S bar with U, then you will get the corresponding quark of quark structure of K plus. Similarly, let's consider pi minus. This is pi minus. So if you consider pi minus particle, you have D here, already D here, that is the quark. Then which one will be the antiquark? You just check what is the opposite quark. What is the quark coming in the opposite corner of that particular particle, pi minus. Then you can see in this side you have U as the quark. Then you have to put U bar. Then du bar will be the corresponding quark for pi minus. So in the case of meson spin zero mesons, you can just consider this uh, approach to find out which are the quarks corresponding to each particle. And now we'll move to the mesonic resonances. For mesonic resonance also you can do the same procedure. You will get the corresponding quark antiquark pair for the mesons. You can see here you have US bar here. Then just you consider. Let me check if this is U and the opposite you will be having S. Then so all those things are there. You just confirm that for this case also it is working. Now let us consider the case of decouplet, baryonic decouplet. We just check with the case of mesonic resonance also, whether it is coming or not. Now you consider the decouplet. This is a little bit different, but it is very simple. You can see for decouplet, this edges you have triple U, triple D, and triple S. Okay, U, 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 S, 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 and D, D, D as the quark structure. And just to consider this side in this decouplet, to consider U here and D here and S here. Okay, so this side you have 3 Ds, this side you have 3S for omega, and this side you have 3U. And then we move, when you move this side, when you get down to the next particle, for example, sigma star plus, then one of U will become S. One of the U will become S because this side you have S. Okay, you are moving towards S. Then again, if you move further to cascade, I think it is cascade 0, right? Cascade star 0. So in cascades, when it reaches cascade star 0, then one more S will come. One more U will be replaced with S. Then you will get USS because it is coming close to S. Then when it is omega minus, you will have 3S. Similarly, this side also, you have 3D here. And then when you move this side, then one of the down quark will be changed to strange quark. Then this will become DDS. Then again, if you move to cascade minus star or cascade star minus, that is the resonance particle of that cascade particle. And then one more D will be changing to S. Then you will get DSS. Okay. So in this fashion, you can find out the different quark structures inside the particles. In this case, it is baryonic resonance. Now, also, why you have to remember all this quark structure? Because if you know this quark structure of each particle, and if you know what are the different if you know this table, different if you know what is the charge, spin, baryon number of these quarks. So basically, if you know this table for the quarks, their properties, then you can easily find out the properties of each particle. What is the strangeness, what is the baryon number, what is the charge of that particle. All those things can be easily found out by using this table. Okay, so that's about the quark. Also, you have to remember along with this UDS quark, we have other quarks which are top, bottom, and charm. Top, which is represented by T, bottom, and charm. These are other quarks which are also there, and their anti-quarks are also there. That also you have to remember. That is not that much important for the exam point of view. And also we'll be having some other color quarks. I will just explain the color quarks here. So when you consider the, for example, the omega minus case, you have 3 baryons, right? You have 3 baryons which are same. For example, omega minus you have SSS. So in those cases, for example, if you consider omega minus, so if you consider omega minus, you can easily observe that these are having 3 strange particles. So this, strange quarks. If there are 3 strange quarks, then this will violate the Pauli's exclusion principle because each of them will be having spin of half. Okay, so one of them can take plus half, the second one can take minus half, but the third one should not have any of those plus or minus half. because it will violate the Pauli exclusion principle. So in order to uh, avoid this violation of Pauli's exclusion principle, uh, we have introduced another concept which is nothing but the colored quarks. Okay, that concept is colored quarks. So in this case of colored quarks, we are considering different colors for each of these quarks. Okay, and these colors are nothing but red, yellow, and blue. These colors are red, yellow, and blue. So each of the quarks will be having different colors, and if they are different, if they are in different colors, then they will not violate the Pauli's exclusion principle because the color quantum number will be different for those quarks. So we have to be for in order to in order to okay, in this case, yes, in this case also we have a red, yellow, blue are the colors for the quarks. So since they are violating the Pauli exclusion principle, we have introduced this uh, color concept for the quarks, and we associated with that we have the color quantum number. Okay, so we'll be having different uh, numbers or quantum number corresponding to these colors. And if you are having these strange particles like this SSS, they will not obey Pauli's exclusion principle. So in this case, as we discussed, half will be the spin if you are considering first one is plus half and second one is minus half. Then third one will not be able to take plus or minus half because it will violate Pauli's exclusion. So to avoid that, we will have this color code. So if you consider this is red code for this strange one is red code, and the second one is yellow, and third one is blue. Okay, so this red, yellow, blue, they are different. So in this case, it will not violate the Pauli's exclusion principle because one quantum number is different. The color quantum number is different in this scenario. Okay, so for the case of baryons, they are made up of these different colors, and since they are having these three different colors, they will these three different colors will make it as colorless. So all the baryons are colorless particles. Similarly, if you are having a particle and an antiparticle, or a color and an anti-color, that also makes the particle as the colorless particles. Okay, so if one is color and the other one is anti-color, then that will make the particle which is colorless. So one color plus anti-color, this also anti-color make that will give you colorless particle. And all the mesons which are made up of this color, okay, color anti-color combination, color anti-color combination. Okay, so all these hadrons, if you consider, if all hadrons, if you consider, which consist of baryons and mesons, so all those hadrons are colorless particles because if they are baryons, then they will be having three different colors. They will make it colorless. And if you consider they are mesons, then one will be color and the other one will be anti-color. That also make it colorless. Okay. So in that case, all the hadrons will be colorless particles. And another thing that we have to discuss in this section is that we have a low, or we can consider it as uh, another theory, which is color chromodynamics, quantum, quantum, color, quantum chromodynamics. These are not that much important for examination point of view, but that's why I'm not going to detail the description of these things. As we are going through a crash course, this much is enough. So this quantum chromodynamics, or you can say this is QCD, so which says that the color is basically this color is the responsible property corresponding to the inter quark force. Inter quark force. As we discussed, these particles are very stable, and these are stable, and these particles, I mean the hadrons. So all these hadrons are made up of quarks. Then how these quarks are tightened up, okay, and that is through this interquark force, and this interquark force, for, for this force there are some carrier particles. These carrier particles are called gluons, okay. The carrier particle associated with this force is called gluons. So these gluons are exchanging between the quarks within the particle. Okay, that in that exchange there will be a very strong force that develop a strong force, and because of that strong force, these particles are basically highly stable. So, what are the different gluons? What are the different gluons that are responsible for this quark force between each of these quarks? There are a total of 8 gluons, total of 8 gluons, and in this 8 gluons, 6 gluons are total of 8 gluons. In that 8 gluons, 6 gluons are 6 gluons. These 6 gluons are color changing gluons. Color changing gluons, and 2 gluons which are color preserving gluons. So all this interchange of these gluons will result in that interquark force. Okay, but when they interchange these quarks, this color, sorry, these gluons, there will be some change in color. If it is by these 6 gluons which are changing, interchanging, then there will be change in color. If these 2 gluons are changing, interchanging between the quarks, then there will be no change in color, or they are preserving colors. Okay, so the 6 color changing gluons are, I will just list it out. Just list it out here. So these are GRB prime. Then you have GRY prime. Then you have GY bar, sorry, YB bar. Then GYR bar. Then GBR bar. Then GBY bar. So these are the color changing gluons. At the same time, you have color preserving gluons, which are G0 and G0 dash. These are the color preserving gluons. So if these gluons are interchanging between the quarks, they will not change colors. But if these 6 gluons are interchanging between the quarks, then they will change color. For example, if you consider one up quark which is having color blue. So this is the representation up quark with U, and B is standing for color. So UB, that is the up quark with the color blue, which is decaying into an up, which is going to become an up quark with the red color, plus a release of a gluon with BR dash, blue and anti-red color. Okay. Now, another example, if you can consider here, D, that is a down quark. with red color, which is or which is absorbing. I will just this that one, which is absorbing one gluon. So Dr plus. Let's say this. If you are considering GBr dash, gluon with the blue and anti-red color. So this will become this anti-red and this red will cancel each other. Then that will become D with the blue color. D with the blue color. Similarly, you can see this one is blue. So this R and R will cancel each other. Sorry, R and anti-color, anti-red. You can see here what is happening here. This is there is one blue color. Okay, so that blue color is R plus BR. Okay, so this R prime and this R will be cancelled and that will give you blue color. Okay, so this is how that particular blue up cork becoming a red cork and a gluon with red, blue and anti-red color. Similarly, this blue and anti-red colored gluon is absorbed by a down cork with red color, as you can see here in the second case. And this red and anti-red cancel each other, and that will become, this down cork will become a down cork of blue color. Okay, so in this case, this red plus Br prime, that will become bluish. Okay, so that is the interaction. You can also represent this particular interaction with a series. Similarly, if you consider, for example, G0, some if you consider some other cases, G0 is responsible, or G0 dash also are responsible for change of the quarks without changing the color of the quark. So when G0 or G0 dash is changing, is is the interacting particle between the quarks, then the color will be preserved. The color will not be changed. Okay? Color will be preserved. Okay, so that's about the color or quantum chromodynamics and color quarks. Also, these quarks are confined. You cannot separate the quarks, or you cannot get a single quark. So, for example, if you consider the mesons, there will be a quark anti-quark pair. For example, if you are having up quark and a anti-strange quark, if you want to separate this, that is impossible. That is not possible. If you want to give some energy to this quark anti-quark pair, and if you try to separate them, that will never happen, because you have to give some enough energy, because this force is very strong, and you have to give some very high energy to separate these two. But that high energy is enough to create a quark anti-quark pair. Okay, so if you separate these two and then try to separate these two, then suppose this you can represent by Feynman diagram, and so suppose you have a US bar, something like this. Okay. These are some theoretical aspects. We don't have to discuss all these things. So let's say so this is US bar representation of this thing, and then if you after giving enough energy, if you are trying to separate these two, so if you have given some energy and you are trying to separate these two, but this will never separate. After breaking of this bond or this force between them, and if you give enough energy, then another and quark anti-quark pair will be created in between this. So one UD plus, along with this, we might have some D plus that S bar. I'm just writing it. This may not be the real action, but I'm just giving you some hint. So this with this particular bond is breaking, then a D bar. You can see here a D bar pair, a quark anti-quark pair is created because of that high energy. Because of that high energy, this is created and that is bonded again with U and S bond. So you will never get a quark, single quark, and this particular property is called quark confinement or confined quarks. Okay, so you will never get a single quark. Okay, so that's all about the quarks model. I have only discussed the important portion that may come in these exams, but this kind of questions are not asked. Okay, so this much is enough for the course. So I will just do some examples now. Some of the questions, some questions I will give some questions regarding the conservation of the particles, conservation laws, etc. for the particles. Okay. So let me give you an example. We have done some problems in the last section. Okay, I will also give you some hint. I'll just take one. Side is okay. So let's consider some other important tip. One is that if you consider different interaction, one easiest way to check whether the interaction is strong, electromagnetic, or weak. So if you consider strong interaction, so first thing that you have to check is whether all the particles are hadrons or not. Whether all the particles, all the particles are hadrons. All are hadrons. If all are hadrons, then the interaction will be strong. Okay, and if you consider the next hadrons, we have only hadrons. This is required. And the second point, if it is strong interaction, then there will be associated production. There will be, if you are having associated production, associated production. Okay. Then also this is for strange particle. Okay, for strange particle. So if you are having strange particles which are produced in that particular interaction, then also it will be a strong interaction. Okay, it will be a strong interaction. Also, we have to consider there should not be any leptons. Okay, no leptons here. There should not be any leptons. So in that case also, because we have already discussed, the strange particles are uh, always created in strong interaction. So when it is or produced in strong interaction, so when it is associated production of strange particle, then that might be a strong interaction. And then you have electromagnetic interaction. Electromagnetic interaction. For the case of electromagnetic interaction, first you have to consider if gamma particles are present or if photons are present. You can consider photon or gamma. If gamma particles, gamma is present, then that particular interaction will be electromagnetic interaction. Okay. And another point is particle and antiparticle. If particle and antiparticles are present on one side, any of the side, one of the side of the interaction, if particle and its antiparticle is present, then the corresponding interaction will be electromagnetic interaction. And when you consider weak interaction, you can also consider for these cases, you can consider that isospin strangeness values for weak interaction, delta S will be 0, delta I will be 0, delta I3 also will be 0. Okay, so that also will be, that conditions are there that we have discussed in the last class. But this is somewhat easiest. Okay, so in the case of weak interaction, so in this any lepton presence, electron present in that interaction, then corresponding interaction, mm, there is high possibility for weak interaction. That will be weak interaction. Then the second one is that if you consider the case of strange decay, strange particle decay, if any strange particle are decaying, not interaction we are talking about here, we are talking about the decaying of particle, not interaction. So if the strange particle decay process, then that will be weak interaction, because the strange particle will be always decay in weak interaction, through weak interaction. Okay? So these are the hints corresponding to those the type of different interaction. Sometimes they will ask in the exams. So in that case, you can answer by using this criteria. So we'll just discuss some problems now. Okay, so let us consider some problems. Uh, we will do some different types of problems. One is finding out missing particle, and the other one is conservation, whether the particular reaction is possible or not, or problems may come like the types of interactions. So there are different types. So first we'll go with the types of interaction. Okay, find out whether which type of interaction it is. The given interaction, which type of interaction it is. So let us consider, for example, in the first case, let us consider an interaction. I will give example. Okay, so K minus plus P, that is becoming sigma minus plus phi plus. This is an interaction. We have to find out which type of interaction it is. Okay, now you just consider the previous table or the hints that we have given. You can see here, this is K minus interacting with a proton, and you are getting sigma minus and phi plus, sigma minus and phi plus. Now you can see all the particles which are present here, which are hadrons. All the particles which are present here are hadrons. So we have already discussed if all the particles are hadrons, then that will be strong interaction. So in this case, this particular interaction will be directly, you can say this is strong interaction, because all the particles present here, this is strong interaction because all the particles are present, particles present here are hadrons. K minus is meson, P is baryon, sigma is meson, phi is meson. So, sorry, sigma is baryon, phi is meson. So, all are baryons and mesons which are hadrons. So, if all these particles are hadrons in that interaction, then that will be a strong interaction. Okay. So, let's take the second example. Let's take nu minus plus nu plus gives K minus K minus plus K plus. What type of interaction will be? This will be electromagnetic interaction. Electromagnetic interaction. Why? Because on the side you can see particle antiparticle pair. In this case, we have on both sides we have antiparticle particle antiparticle pair. You have mu minus and mu plus on this side. You have K minus K plus. So these are particle antiparticle pair. Okay. So particle antiparticle pair. We'll write it here. Particle plus antiparticle. Okay. Antiparticle. So then you can directly say that this is electromagnetic. This is strong because all are hadrons here. All are hadrons. All are hadrons. I will just give you one example for weak. One more example for weak interaction. You can work out this further. So this is example sigma plus. Sigma plus is decaying into P plus phi 0. So directly you can say this is weak interaction because this sigma plus is a strange particle. Strange particles. Strange particles are all the hyperons and kaons. Okay, all the hyperons and kaons. So this particular one is weak interaction. This particular one is weak interaction. Why it is weak? Because this is decay of strange particle. Strange particle. So all these are taken from the previous hints that we have given, corresponding to different type of decay or interactions. So the decay of strange particle. So that will give you weak interaction. Okay, see, so these are the examples. This is one previous year asked. These are previously asked questions. Okay, so just giving you it as some example. Now we will go to the other type. One is whether this particular interaction is conserved or not. Okay, conserved or not type questions. So conserved or not. So let us take an example. Let's say pi plus becoming E plus and neutrino. So in this case, you have to check all the conservation laws: baryon number, lepton number, charge conservation, angular momentum, and the energy conservation. All those things. So let us take pi plus. For the case of pi plus, you can see. You can just check the lepton number first. Lepton number conservation. You can take a electron lepton number, neon lepton number, like that also. So in this case, we have electron. So electron lepton number will be 0 here, and this is equal to, this is positron. E plus is positron, right? So this is sorry, this is minus 1 for positron. That is antiparticle of electron. So for that, the lepton number will be minus 1. Antiparticle minus 1 plus this is plus 1, right? Because it is not antiparticle, so the lepton number will be plus 1. So on both sides we have 0. Lepton number is 0, so lepton number will be conserved. Then if you consider baryon number, baryons are not present here, right? So all are mesons and leptons, so baryon number will be 0 on both sides. So baryon number is conserved. What about charge? Charge will be plus plus. So this is plus 1 equal to plus 1. Neutron not charged. So charge is also conserved. Then you can also check if you want angular momentum, you can check. Okay, in that case, you have to check whether the uh, angular momentum is conserved or not. So you can check the angular momentum of the pi plus. So for pi plus, where you have to check that, you can check that in that octet that we have discussed earlier. So let me show you that. So in this structure, you have octet of semi-stable mesons. You have the spin which is equal to 0. You can see the spin is equal to 0 here, octet of semi-stable meson. And there you have that pi. You can see pi is here. So spin is 0 for this octet of or this particular meson. So for pi meson, spin is 0. So we'll just take. Yeah. So for pi, it is 0. So you can take it as 0. Okay. So if you consider spin, that is for angular momentum conservation, then pi it is 0. Then you have E plus, that is antiparticle. So you can take it as minus half, then this can be taken as half. That will make it as 0. So angular momentum that is conserved. Similarly, you can consider energy also. For energy, you have to consider the mass of individual particles. Let me check the table. You can see in this table, you can just take a screenshot or something. These are some of the examples for the masses corresponding to each particle. I think pi minus is not there. You can calculate by using that UDS, up quark, down quark, and strange quark. That is how, in the case of pi plus, there will be two quarks, add their masses, okay, and equate that with the other side, okay. Consider the other side mass of those positron and neutrino, and check whether it is coming almost similar. Okay, but in that case, if energy is released with this particle, then that also will be have to be considered in that particular case. But in the case of decay process, anyway, this one should have a larger mass and almost equal to the other side, and the energy will also be conserved. Okay, that you can check with the mass of the particle, and this so almost all of them are conserved. So this particular interaction that will be conserved. Okay, so if you consider some other case, let me say. In this case, this all for the free particle. Okay, these are for free particles. Let us consider another example. Uh, lambda zero, lambda zero. I will just zoom it a little bit. Okay. So lambda zero, this is going to become. You can also check parity. Okay, parity. Whether in this case also you can check whether parity is considered. All those things are. In the case of I think in weak interaction, parity will not be considered also. Okay, so that have to keep in mind some cases that is not considered. Anyway, so you have to check only this much spin, angular momentum, quantum number, the energy, the charge, baryon number, lepton number. These things you check, and if all these things are conserved, then the interaction is possible. Okay. So if you consider lambda zero, in this case, lambda zero becoming a proton plus a positron plus a neutrino, electron neutrino. So in this case also you can check the different conservation laws. Let's take the conservation law for leptons. Lepton. So for lepton number conservation, this is 0. Sorry, for so lepton number conservation. So this is 0. It is baryon, and this is 0 baryon. This is -1. This is +1. So that is conserved. Now for baryon number conservation, you can take it as B or A, both are representing baryon number. So this is lambda 0, 1. Then here also you have 1, then plus 0, plus 0. This is conserved. Both side you have 1, so delta B is 0. And then Q, charge is 0 here. Here plus plus, so plus 1, plus 1, plus 0. Charge for neutron is 0. So this is not conserved. So in this case, this interaction is not conserved because it is not, charge is not conserved, or this interaction is not possible because charge is not conserved in this interaction. Another interaction which is not conserved because of the energy that I will just show you by that particular interaction. These are for free particles. Okay. So for example, in the case of a free proton, for free particle, I'm saying free particle. This is important because in some other cases this is possible. So proton becoming neutron plus A plus positron. plus a neutrino. So inside the nucleus, this particular interaction that is possible. But when you consider it as a free particle, when you consider that as a free particle, this interaction it will not be possible. Why it is not possible? Because this interaction, if you consider, if you check the lepton number, what will happen? Lepton number that will be 0 here. Then on the other side you have 0 plus. This one is minus 1. This one is plus 1. So lepton number is conserved. Barium number, if you consider 1 here, then this one is also 1 plus 0 plus 0. Barium number is conserved. Charge, if you consider, charge will be for proton, this is plus 1, and for neutron 0, E plus plus 1, for neutrino 0, so charge is conserved. So if you consider uh, the spin also you can see that will be conserved. If you check, this will be half spin, this will be half, this will be having minus half, and this will be having half, so that will cancel each other, and there will be neutron and proton will be half spin. That is possible. Okay, so you can take different composition or combinations of spin, then you can have one of them will be possible in this case. So angular momentum, if you check angular momentum, that one also will be conserved. But when you consider the energy, you consider energy, which means you have to consider the mass of proton and mass of neutron and positron, etc. The mass of proton, if you consider with that of mass of neutron, when you consider this mass of proton will be lesser than mass of neutron. That will be lesser than mass of neutron. And also you have E plus and neutrino on this side. So you have more mass on this side. So that for free particle that is not possible. With the presence of that or inside that nucleus, okay, with the presence of that heavy nucleus, that is in that case that is possible. This particle decay is possible, but as a free particle, free proton, this particular decay is not possible because proton is having less mass as compared to neutron, and also you have one more particle E plus on the other side, so the energy will not be conserved in this case. So the mass is not similar on both sides. So this particular interaction is not possible as free interaction. Okay, as proton as free particle, that is not possible. But in the case inside the nucleus, yes, that is possible. Okay, that you have to keep in mind. So this type of questions may come. So you just check the different conservation laws like this, and you can say whether the interaction, whether it is possible or probable. Okay, and we will discuss one problem that is missing particle. Let's take one simple case. Let's take K minus for missing particle. Missing particle problem. So let us consider K minus K1 with minus charge plus proton that is that will give you K plus one missing particle, which we represent it as X, missing particle. So X is missing particle here. So we have to find out which one is missing particle here, and the interaction is possible, or this particular interaction is possible, or which is probable. So we don't have to consider the whether it will we have to we don't have to check the conservation laws here. It is given this particular interaction is possible or probable, which means all those conservation laws are valid here, which is obeyed, and in that scenario, which one will be what will be the missing particle X. Okay, then you just check the conservation charge conservation. The conservation means the charge is conserved here because this interaction is possible or probable, which is given in the question. So charge will be conserved in this interaction. So if you take Q, then this one will be minus 1, this one is plus 1. Okay, so total charge in this side is 0, this side is plus 1. So the missing particle should have a charge of minus 1, then only this charge will be conserved. So we have a particle with charge -1. Okay, -1 means minus the charge of, which is nothing but the charge of the electron. Okay, -1 is charge of the electron. And then you consider lepton number. Okay, lepton number as a whole, if you consider this is meson, this is 0, this is proton, that is also having 0 lepton number because it is value. Again, k meson, so this is 0. This is, so the missing particle should also have lepton number which is 0, which will give you the missing particle is, sorry, the missing particle is not a lepton. This will give you a conclusion that the missing particle is not lepton because lepton number is 0. Lepton number has to be 0 for the missing particle. Then only lepton number will be conserved. So lepton not a lepton. Not a lepton. Not lepton. Okay, then you consider baryon number. For the case of baryon number, what will be the values? So it has to be conserved. Okay, so baryon number for k, it is meson, so this is 0. Next one is 1 because it is baryon. K plus is again 0. Okay, so then this one must be 1. So which means that it is a baryon. So the missing particle is a baryon, not a lepton, and it is having a charge of minus. Charge of minus. Then you consider the case of, you can consider strangeness, you can consider isospin, all those things. Okay. For most of the cases, they will give the strangeness. If it is given as strangeness, it is conserved. Then you have to take delta S is equal to 0. Delta S is equal to 0. If, for example, it is given the interaction is strong interaction, then delta S you can take it as 0. If it is given the interaction is weak interaction, then you have to take delta S is non-zero, plus or minus 1 value. Okay, so for weak interaction, so all those things are there. So depending on the question, that values will be different. Okay, so if it is only conserved and all these values are conserved, then you can also take delta S is equal to 0 in this particular case, and which means that that must be a strong interaction or is that electromagnetic interaction. In that case, also you have that delta S is equal to 0, delta E equal to 0, delta E3 not equal to 0. That conditions that you have to consider. Different conditions are. So if you consider strangeness, okay, so in this case it is given that this particular interaction is strong interaction or delta S is equal to 0, and so since all the parameters which are conserved in this particular interaction, so delta S has to be 0 here. So in that case, if you put S strangeness, what is K minus strange, whether it is strange particle? K minus is strange particle, yes, it is strange particle. Strange particles are kaons and hyperons. Okay, I'm recording that. So corresponding for K minus, it is having -1, strangeness of -1. You can check that object of semi-stable baryons. You can see what is the strangeness of, sorry, semi-stable mesons. You can see what is the strangeness of K minus. And proton, there is no strangeness because protons are not strange particles, they are nucleons. Okay. Then K plus, we have a strangeness of +1. Okay. Yes. Then in order to make this strangeness conserved, this one should have -2. The missing particle should have a strangeness of -2. So strangeness of the missing particle is -2, and it is a baryon, and it is having a charge of -1. And if you conclude from this, if you check which particle is having all these properties, then you will get that cascade or psi particle, which is the psi minus, or the scatter minus is corresponding particle, which is strangeness -2, baryon number 1, and charge -1. Okay, so this is how you will find out the missing particle. I'm just giving you some example. You can work out with some other problems to find out the missing part. Okay, now we'll discuss some problem with the quark model. We'll check the problem. Let me see the quark model here. Yeah. So one question which is previously asked, which is given as okay, the question is like this: a particle which is composite of three quarks. A particle with three quarks, three quarks, UDS, has electric charge, comma, spin, strangeness, equal to, respectively equal to. So I'm just making it short, equal to, and there are different options. Okay, so A, 1, half, half, minus 1, then option B, 0, 0, minus 1, then option C. This is previous question. So 0, half, and minus 1, then D, minus 1, minus 1, minus 1, minus half, and plus 1. So these are the given options. Now, just you have to check. It is given that the given particle is having quark structure of UDS. Now, what you have to do, you have to remember that label with up, down, and strange quarks, and correspondingly, what were the different charge? For example, if you consider charge, then you have to consider, for example, UDS you consider. And for charge, what will be the charge of UDS? This will be having 2 by 3 E, right? And for down torque, it is minus 1 by 3 E. This is minus 1 by 3 E, right? And for spin value, this is half, this is half, this is half. And then third one is strangeness, right? Strangeness value. For up torque 0, 0, and only strange torque it is minus 1. Okay. Then you take total of this. So total means you are having UDS. So you have to take then total of UDS. Okay. So total will be total for UDS, that will be here 0 for charge. For spin, that will be 1 by 2. 1 by 2 plus 1 by 2 will give you 1 and 0 combinations. Okay. 1 by 2 plus or minus 1 by 2. That will give you spin value 1 comma 0 total. Okay, then you have one more 1 by 2. When you add that 1 by 2 with this 1, you will get 1 by 2 again. From this 1 comma 0, add 1 by 2 with this 1 and 0. That will give you, when you add with this, then you will get 1 plus 1 by 2 is 3 by 2. Then 0 plus 1 by 2 is 1 by 2. Right? Then you subtract. 1 minus 1 by 2 is again 1 by 2. 0 minus 1 by 2 is minus 1 by 2. That will become 1 by 2 itself because minus is not possible. Total angular momentum, that will be plus. Okay, so only 3 by 2 and 1 by 2 will be there. Or you can take magnitude of 1 minus 1 by 2 and 0 minus 1 by 2. So in that case also you get 1 by 2. So 3 by 2 and 1 by 2 are possible. So total of spin will be 3 by 2. Either 3 by 2 or 1 by 2 are possible. Then strangeness total is minus 1. Okay, so what is the option? This one will be the option. Charge is 0. So only this B and C are right answer. Then spin value is either 3 by 2 or 1 by 2. So you can take 1 by 2. So C will be the correct option. this is a previous year question from core model, or they can also ask direct questions. They can also ask direct question like they will give some particle and ask which one is the corresponding quark model. Okay, such question also may come. Okay, so we have covered all the sections which are important for you, and I think yeah, one more I have to discuss that fission and fusion section. Right? So fission and fusion, I will just give you something. These things are not important. We have already discussed the fission and fusion section in the last class. The important things from the fission and fusion section, which are nothing but the K factor formula in the case of fission, and the Lawson criteria in the case of fusion interaction. So when you consider fission interaction or fission process, you will be having a heavy nucleus, let's say X, that will split into two lighter nucleus, let's say Y and Z, with some energy release of some energy. So basically, this fission will happen for heavy nucleus, which are having very low binding energy per nucleon. So when you consider that binding energy per nucleon curve, okay, so I think we have already discussed all these things in the last class. So the nucleus which are coming in that extreme end of that curve, take this one, this portion that will undergo fission and that will reduce its size, and it will become lighter nuclei, and that will increase the binding energy per nucleon value of those nucleus, and that will occur more stability, because here we have very less binding energy per nucleon. Once it will split into two nucleons, so two nuclei, if they are, let's say these are Y and Z, that are coming in this position, this is X nucleus, which are heavy, which is heavy. So when that will become Y and Z, this will be having more binding energy per nucleon value, that will increase the stability of the nucleus. So that is the process which is happening for this particular fission, in this particular fission interaction. So mostly they will ask this Q value. So that Q value you can easily calculate as we discussed in the earlier classes. Q value is nothing but you can consider mass of X and take mass of Y plus mass of Z together. Okay, and the difference of this, that is mass effect, multiply this with C square. That will give you energy in joules. Or you can take each of these masses in atomic mass unit. If it is in atomic mass unit, for let's say E30, in and masses are in AMU, atomic mass unit, then you can consider small as mass of X, mass of Y plus mass of Z, okay, Z nucleus. Multiply this with 931.5 megaelectron. So this much of megaelectron. That is the energy released in the fission interaction. Energy released in the fission interaction. Okay. So at the same time, if you look at the K factor formula, in that case, you have to consider the fission interaction, fission, what is that, fission reactor, nuclear fission reactor, and in that nuclear fission reactor will be having different components. So all these things are theoretical aspects. Okay, so that is not that much important for the exam point of view. So that's why I'm not going to discuss those things. But you just check. I will just give you something. Just check that four-factor formula. Four-factor formula in that fission reactor, or it is also called K-factor formula. K-factor formula. that it is also not that much important, but just to check that, okay, for the case of fission. For fusion, we have something to discuss. So in the case of fusion, two lighter nuclei will combine to form heavy nucleus. For fusion, in the case of nuclear fusion, two lighter nuclei combine to form a heavy nucleus. Okay, so that is the interaction. So just opposite of that fission interaction. In this case, we have lighter nuclei which are combining to form that heavy nucleus. Heavy nucleus. So in this case, okay, so let us consider X and Y are the lighter nucleus, or you can just take the in the case of previous case. In the previous case, you have Y plus Z, right? So Y plus Z, which are the lighter nuclei, which is going to become X. X is heavy nucleus, but not that extreme end. Okay. So this actually happens in that binding energy per nucleon curve. I will write here. Okay. So if you consider the binding energy per nucleon curve, in that curve, we have to consider this lower portion of that curve. So this side, again, this one is binding energy per nucleon. This side you have mass number, and the nucleus at this side, they are having less binding energy. Let's say this side you have this Y and Z nucleus, Y and Z. They combine to form a nucleus somewhere here, that is X, so that their binding energy per nucleon value will be increased. Okay, so this is why nuclear fusion is happening. Nuclear fusion is happening, and in this case also you have different lighter nuclei combining to form heavy nucleus, and that will also release energy. In this case also, you'll be having energy released, and if you want to find out what is the energy released, then you have to find out if again this is in the atomic mass unit, masses are in the atomic mass unit, then you can just take mass of X plus mass of Y plus mass of Z. Okay, this you have to minus mass of X, then multiply this with 931.5 mega electron volt. You'll get the energy released in that particular interaction for nuclear fusion. Now you have another important thing, that is fusion in stars. Okay, so fusion in stars. First, you have to consider fusion in sun, fusion in stars. So when you consider fusion in stars, there are many other theoretical aspects. Okay, the nuclear fusion reaction is not yet fusion reactor is not yet came into existence, because the energy required or the energy given to that particular nuclear reactor is more as compared to the energy which is coming out from that reactor, and there are many difficulties of constructing those nuclear reactors, nuclear fusion reactor, because we have to have a very high temperature for the nuclear fusion to happen. When you consider in the case of sun, it is a very huge, 10 raised to 9. We need 10 raised to 9 Kelvin, but in sun it is 10 raised to 7 Kelvin, and because of that high density, since that high density in sun, even the temperature is a little less as compared to the obtained theoretical value, the fusion is possible. Even the sun is having 10 raised to 7 Kelvin of that temperature. So that in even that much of temperature is enough to have that fusion reaction in sun because of high density. Okay. So all those things are there. These are theoretical side, and then we have to make such kind of scenario in Earth to make the nuclear fusion reactor. And we will consider thermonuclear power station because we will consider first the plasma state after giving enough temperature for the fuel, which is the nuclei which are fusing. Okay. So if you provide enough temperature, then that electrons and all those things will be separated from that atoms, and that will become in a plasma state. Okay, all those things are there. Then you will give enough energy to that plasma state. Then random collision will happen, and in that random collisions, if it crosses that Lawson criteria, then you can get enough energy output. Okay, that fission will happen. So there are different theoretical aspects. There are confinement techniques. Different types of confinement techniques are there. Magnetic confinements are there. Then you come up with a tokamak design. All those things are there. Okay, in that fusion. But for examination point of view, you have to think only about fusion in stars. So in fusion, when you consider fusion in star, first you have to consider sun. In case of sun, we have the PP cycle, so-called PP cycle or proton-proton cycle. This is the responsible interaction or nuclear fusion reactor reaction, nuclear fusion reaction, which is happening in case of inside sun. If you consider heavy nucleus, then you will be having CNO cycle. You will be having CNO cycle, carbon, nitrogen, oxygen cycle for heavy nucleus. Uh, Sorry, heavy stars, okay, which are having much more massive than that of sun. Then you have this carbon, nitrogen, oxygen cycle, which is responsible for the energy uh, release, okay, in that particular star. So in PP cycle, I will just show you how this is happening, and I will show you the total energy release. First one is one proton which will be interacting with another proton, that will give you a neutron plus a positron plus neutrino, electron neutrino. Then this neutron will interact one more proton, and that will give you three helium 3 plus one gamma radiation. And after this interaction, the 69 percentage time, this particular interaction will happen. For 69 percentage, this 3 helium 2 combined with another 3 helium 3 nucleus to form helium 4 plus 2 proton, 2 proton. Okay, and remaining 31 percentage of time, 31 percentage, this 3 helium can interact with helium 4 to form beryllium 4 and 7 plus some gamma radiation. And after this interaction 97 almost or you can take 99.7 percentage, this is 99.7 percentage of time, this is only 0.3 percentage of time. And this will happen, this beryllium 7 that will interact with one electron to form lithium 7 and 3 plus neutrino. Okay, again this lithium 7 lithium that will undergo the reaction, lithium 7 then 3. This will interact with one proton, and that will become 2 helium. And for 0.3 percentage of time, this beryllium 7 4 that will interact with the proton, directly with the proton, and that will give you boron 8 and 5 plus gamma, and this boron again that will become 8 5, that will become beryllium 8, beryllium 8 and 4 plus E plus. This is nothing but a positive beta decay process electron, and then that beryllium 8 will become 2 helium 4. So these are different types of interaction. Okay, and this first one is called PP1 cycle. First one that we have discussed here, that is the 60% of time, 69% of time. So this one is called a PP1 cycle, PP1 cycle, this one. And this one is called a PP2 cycle, PP2 cycle, this one. And this is called a PP3 cycle. Third one is called PP3 cycle. So all this will happen, but the probability for them will be different. As you can see from here, probability is different. And in this interactions, the energy, the final, in all these interaction, energy will be released. Okay, so I am not going to write you can just check how much energy is released in each of these interaction. But I will just give you as a total how much will be the released energy. That released energy will be around total energy. I'm talking about total energy released, total energy. So for each step there will be energy release. Total energy released will be, you can just calculate that. There are many other figures or pictures which will also give you this energy in each of these interactions or in this fusion steps. So this is 26.7 mega electron volt. That is the energy released in this particular interaction. Also, you have to balance this equation to get the final output of the fusion interaction. So you just consider the total value, total how many protons are used, and what are the result. You will be anyway. You will be getting 2 helium nucleus at the end, 2 helium nucleus at the end, and in between you will be having different you can see here you have positron which is released here, you have neutron which is released here. So you can balance this equation and you will get the final interaction, finally how many number of protons are used and how many helium nucleus are produced, that you can check later. So this is the PP cycle, and in the case of CNO cycle, there also you'll be having the same energy, which is the total energy that released will be the same. There is no difference. That is 26.7 mega electron volt. So in the case of CNO cycle, we will just draw it here. You will be having carbon 12, and this carbon 12 interact with a proton H1, okay, and that will form. You can also use you can just check some figures so that you can easily understand that I didn't include a figure here. So that's why it is little. So this carbon 12 interact with one proton, that will produce one neutron, sorry, nitrogen, one nitrogen and gamma radiation. Okay, and this nitrogen will decay into one again. This nitrogen will become carbon 13. carbon 13. Along with that, it will release the neutrino. I think this one will be, yeah, neutrino. And also you have a positron. So I will just, okay, I will just put it here. E plus positron. And then this carbon that will be absorbing, that absorb a proton here. Then that will become a nitrogen. Nitrogen, this one is nitrogen 13. This one is nitrogen 13. This one is nitrogen 14. This one will become nitrogen 14. Okay. And this nitrogen 14 that is interacting with a proton. That will interact with a proton, another proton. And that will give you oxygen and gamma particles. So this is oxygen, and along with this, it will release one gamma particle. Okay. This is oxygen 15, oxygen 15, and this oxygen 15 will yeah, that will become, so oxygen 15 will become what, nitrogen 15, nitrogen 15, along with the release of this is neutrino and a positron plus. Then that nitrogen 15 will become again carbon 12. So this nitrogen will be taken one proton and become carbon 12, and this carbon 12, in this process it will release helium nucleus. In this process it will release one helium 4 nucleus. You can just check the proton number. Once it will release the helium nucleus, it will become carbon 12. Okay, so N15, that will absorb one proton and it will become carbon 12 plus helium nucleus. Okay, so this is the total of CNO cycle, what is happening in the heavy or massive stars. So you can again consider the energy, total energy released in these interactions, total interaction is also 26.7. Here also you can calculate how many, you can see 4 protons are used. Okay, so 4 protons are used in this interaction. 4 protons are used. Then you count how many, what else used here? I think 1 proton, 2 proton, only 4 proton. That will give you 4 helium 4 nucleus, right? Helium 4. Then 4 protons are used here, and helium 4, then 2 electron neutrino plus 2 positron, and gamma particle also. Right, two positron, 2 neutrino, electron neutrino, and 2 gamma particles are there. Yes. You just check this final equation. So 4 protons are used. 1 helium nucleus is created at the final output, and we have 2 E plus, 2 gamma, 2 neutrino. Okay, and this entire, this is a total. Okay, so this total interaction will give you plus release of energy Q, that is nothing but the value 26.7. Okay, so this is about CNO cycle. So these two are the important fusion interaction that will happen in sun and other stars. Okay, in sun and other stars. So maybe some questions may come from this side. They will give some interaction and find out they will ask, find out what is the energy released. Or in I think one of the question was this interaction, this interaction, or they have asked how many energy is required to split a helium-3 nucleus into uh, a proton and a deuteron. That is this interaction. Okay, so that's just the opposite of this. They are asking how many energy are required or photon. So that's just opposite. For example, if you consider a gamma photon interacting with a helium 3, how many energy required for this particular interaction to release a proton and a helium nucleus, a proton and a deuteron, a proton and deuteron, okay, a proton and a deuteron. So this was the question, how much energy is required, okay. So in this case, you can see this proton is nothing but H11, and deuteron we have H21. Okay, so in this case, they are asking just opposite of this interaction. You can see here, opposite of this interaction. How many energy? So how much energy is released in this interaction? This proton, which is sorry, deuteron, which is combining with its proton, and that will form helium-3 plus gamma. And how much energy is released in this interaction? So this energy release that is required to form this deuteron and proton. So the question is how much energy is required for this gamma photon when it interacts with the helium-3 to produce this proton and deuteron. Just you have to calculate the differences in mass of this interaction and multiply that with 931.5 megaelectron volt, then you will get the energy released, energy required. So okay, so it is simple. So just opposite to this particular interaction in the PP cycle, they are asking. Yeah, so this kind of question may come. So that's all about the nuclear physics. I hope we have covered all the portions, important sections in this crash course. So I hope very good success in your exams. Okay, thank you.